In one of our previous lessons, we looked at expanding special products. For example, we looked at what happens if we multiply a binomial by itself. So a plus b all to the exponent of 2. And we found there was a shortcut: square the first, double the product, and square the last. So if we have a quadratic that has a perfect square on the ends, so a perfect square is a term that you can square root and get a nice answer to, or it can be written as something to the exponent of 2. And if you were to take those square roots, multiply them, and double them, you would get the middle term. Then we know that the quick way to factor it would be to factor it as a perfect square trinomial. Similarly, if you had a subtract in between, a perfect square on either end of your trinomial, and the middle term being twice the product of those square roots, with a subtract means you have the format of a minus b all to the exponent of 2. If you notice your quadratic is a difference, so difference means subtract, a difference of two things that you can square root, that's called a difference of squares, then it will factor as the product of two binomial conjugates. So it's the working backwards to what you did in your previous lesson. You can always just use the decomposition method with any one of these cases, but if you recognize the special case, it can simplify or shorten up your work and make it more quick to complete the question. So we're going to factor these following trinomials using the pattern above. So our patterns above, if I have a trinomial with 3 terms, I want to look at that first term and the last term. Are those things we can square root and get a nice answer to? Well, yes. X squared square rooted is just x, and 9 square rooted is just 3. If I take the x and the 3 and multiply them together, I would get 3x, and if I double that, that gives me my 6x here. So this will factor as x plus 3 to the exponent of 2. If I were to be nice, write that out twice and expand and simplify, I would get x squared plus 6x plus 9. In my second example, I have a difference of two things that are perfect squares. I can square root x squared and get x. I can square root 100 and get 10. So that means my product is going to be the binomial conjugates. Square root the first, I put it at the beginnings of the brackets. Square root the last, it goes at the ends of the brackets, and I make 1 minus and 1 a plus. Or I could do x plus 10 times x minus 10. Perfect square on part C, perfect square. Square root of 36 is just 6. I have a minus here. I'm going to square root the first term and get d. I'm going to square root the last term and get 6. And I'm going to take that sign from the middle, all to the exponent of 2. But I'm also going to check. If I take the product of these two, I would get minus 6d. And if I double it, I get my minus 12d. So I know that that works. That's supposed to be a check mark. That works. Part D, we have a subtract, so it's a difference. Can I square root 98 and get a nice answer? Can I square root 162 and get a nice answer? Oh, no, it doesn't work out nice. But those are both even numbers. I have a common factor here, so I'm actually going to common factor 2 out of both of those terms. 98 divided by 2 is 49, and 162 divided by 2 is 81. Now I have a difference of squares inside that bracket. If I square root 49, I get 7 with the m, and if I square root 81, I get a 9, and I'm going to have one bracket being 7m minus 9, and then 7m plus 9. So the conjugates will, when I expand and simplify that, I would end up with the middle term canceling out, and that's why my quadratic really only has 2 terms on there. All right, so looking for more patterns here. Always look for that common factor first. If I'm looking at E, I don't have a common factor, but I do notice this is a perfect square and this is a perfect square. If I square root the first, I'm going to get 2x. Square root the last, I get 7. I'm going to take the sign from the middle term. The sign from the middle term is plus, all to the exponent of 2. And then I'm going to check. If I do 2x times 7, and I double that, so I'm going to times that answer by 2. That looks like there we go, I'll put it in brackets, times that by 2. 2x times 7 is 14x. If I double that, that's my 28x. So I know that that does work. My next example, we have a difference, and we have a perfect square and a perfect square. I don't have anything common. I'm going to square root the first. X to the 4 square root it will be an x squared, and I'm going to square root the last. Square root of 625 is 25, and I'm going to have conjugate binomials. They look the same except one's a plus and one's a minus. Now I'm not done yet, actually, because if you look at this first bracket here with the subtract in between, I have another difference of squares. This one, the second one's not a difference. It's not going to factor any further. It's done. But I can square root 4x squared and get 2x. I can square root 25 and get 5. So I'll have two brackets of 2x and a 5, but one's a plus, one's a minus. And I still need the 4x squared plus 25, so that when I expand and simplify that entire products, I would end up with my 16x to the 4 minus 625. Next example, I have a perfect square here. I have a subtract, but here's where I have a fault. I don't have a perfect square on the 7. 7's not something I can square root and get a nice answer to. So this one, I'm not going to be able to factor that because this is not a perfect square. Okay, so it won't factor. All right, if that 7 was a 49 instead, then absolutely. If it was 9y squared minus 49x squared, then absolutely that's going to factor to be 3y, square root of the first, square root of the last, make two brackets that look almost the same except one has a plus and one has a minus, if that were the example here. Okay, the next example, it actually is a difference of squares. Here's your difference. This is a perfect square, and this second one is a perfect square because of the exponent 2. So instead of expanding and simplifying and then trying to factor, I'm going to treat this as a difference of squares. I'm going to square root the first, and I'll get x plus 1. I'm going to square root the last. I get a 2x minus 3. I'm going to make one a plus, but my other bracket has to have a minus. And when I have that minus, I have to subtract that entire second term's square root. So make sure you put that in brackets. And then I'm going to simplify. X plus 2x is 3x's. Plus 1 minus 3 is minus 2. X, this will be minus 2x. Let me actually expand that negative 1 through the bracket. When I expand the minus and the minus 3, it would give me that plus 3. So my simplified factored form will be 3x minus 2 times minus x plus 4. So I could expand and simplify the entire binomial products first, collect like terms, and then treat it like a tricky trinomial to factor. Or I can just treat it like a difference of squares, and it's quite slick that way. All right, we are also now going to use these special patterns to solve some problems here. Determine the value of k, so k is our coefficient of the x. That makes each trinomial a perfect square, meaning I'm going to be able to write that as something to the exponent of 2. So notice the first term is a perfect square and the last term is a perfect square. I could put x here, and the square root of 121 is 11. And I could put a plus in between, or I could put a minus in between. If that is the case, if I have a plus there, I know that k has to work with, or the kx has to be double the product. So my kx is going to equal double the product of the two terms. So double the product of the two terms. So kx is going to equal 22x, which then that means to be equal, the k has to be equal to 22. Or we could have this equaling x take away 11 squared, which then means kx will equal 2 times the x times negative 11, which then means kx would equal negative 22x which then means k would have to be equivalent to the negative 22. So k equals 22 or k equals negative 22. All right, looking at the next one, we know to factor as a perfect square, I would square root that first term. That would be a 9x here. The k is something to the exponent of 2. So we don't know what that's going to be yet. But what we do know is we're also going to take the sign from the middle. So I'm going to put a negative here. So I am going to say that the negative 90x would have to equal 2 times the 9x times the negative question mark. So let's work this out then. 90x would have to equal 2 times 9 would be negative 18 times the question mark times x. So in terms of this, it means that negative 90 would have to equal negative 18 question mark. I'm going to divide both sides by negative 18. And my question mark, then I can figure out. When I calculated that in my calculator, I got my question mark would have to be a 5. So that then means that this is going to equal 9x minus 5 squared, which then if I work backwards, that means that k has to equal 5 squared, which is 25. So if k equals 25, that will factor as a perfect square trinomial. All right, next one. A square of side length x take away 3 is inside of another square of side length 2x plus 5. So let's try and make a square here. So I've got my 2x plus 5 here, and it's a square, so all 4 sides are 2x plus 5. And I have another square inside of that one, and its side lengths are x take away 3. So let's just mark those as equal. Write a factor expression for the area of the region in between the squares. So I'm really looking for this shaded region right here. So see what you can do to come up with that, and then we'll go from there. All right, what I'm thinking in terms of this is I could find the area of the entire large square, which would be 2x minus 5 or 2x plus 5 all squared, and then I could take away the area of the inner square, which is x take away 3 all squared. Now this actually is a difference of squares, so I'm going to factor it as a difference of squares. I'm going to square root the first term. It's going to go at the beginnings of my brackets. I'm going to square root the last term. It's going to go at the ends of my brackets. Oop-a-doop-a-doo. I have an extra bracket there that I shouldn't have. Whoops, that's not what I wanted. There we go. We're going to put that at the ends of the brackets, and then we're going to make one a plus and one a minus. But when I have that minus, I've got to subtract that entire piece. I'm going to simplify my brackets. The first one, collect like terms. I'm going to get 3x plus 2. The second one, when I expand that negative through the bracket, that second bracket, I'm going to have minus x and a plus 3. And then I'm going to collect those like terms in that second bracket, and I get x plus 8. So there's my factored form. Ooh, I made another mistake. That 2 somehow became a 3. There's my factored form of the area, the shaded area, or the area between the two squares. All right, last example. The area of the rectangle is given by this. The length can be this. What is the expression that represents the width of the rectangle? And because I'm almost out of my time limit here, I'm just trying to expedite this. Here's my area expression, and that has to equal the length times the width. And the width is what I need to figure out. So the question is, what do I need to multiply the x by to get the 2x squared? So I'm thinking I would need to multiply that by 2x. And then I have a plus 3 on the end. I have a minus 3 here. What would I need to multiply minus 3 by to get plus 3? I would have to get minus 1 to multiply minus 3 to get plus 3. Now let's check and see, do we get the 7x out of that? If I were to check by expanding and simplifying, I'm going to have a 2x squared minus x minus 6x plus 3, And when I collect these, I get my minus 7x, and I've got that correct. So therefore, the width is 2x minus 1. Or you could go through and just factor this as usual with the adds to and multiplies to. And hopefully one of the factors will be x minus 3 and the other one will be 2x minus 1. So our width is 2x minus 1.